My name is Hernán Ferrari, and with Mauro Cuevas we work at Universidad Austral and CONICET. We will present the work Forces and Binding of Nanoparticles mediated by graphene surface plasmons toward tunable optical matter. First, we detail the regime and approximation we will use and the expressions for the optical forces appearing on dielectric nanoparticles near a graphene plane in our modeling. Next, we give a brief overview of our current results for the optical forces on nanoparticles mediated by surface plasmons. In the third part, we analyze the dynamics of particle systems and how they can achieve a regular structure by bound particles and the edge effects that appear with increasing particle numbers. Finally, we will analyze how the characteristic distance of the particle arrangement can be easily modified by varying the properties of the graphene plane, thus obtaining a tunable optical matter. We consider a system formed by identical spherical and dielectric particles of certain radius and relative permittivity placed above of a plain graphene sheet separating two homogeneous Hall spaces, vacuum and a non-magnetic and isotropic dielectric medium with certain electric permittivity, a linear polarized field and a frequency in the order of the terahertz. Pings from vacuum decide where the nanoparticles are placed in the normal direction with respect to the graphene substrate. We consider the electric field along the x-axis. The graphene parameters, we consider the chemical potential of 0.5 electron volts, carrier scattering rate of 0.1 milli electron volts, and a temperature of 300 Kelvin. With the graphene's conductivity, we can estimate a wavelength for the plasmon induced in the graphene plane in the order of the microns. Taking into account that the size of the particles is smaller than plasmon and photon wavelengths, we can use the dipolar approximation to calculate the time average of the force acting on each particle, where we need the induced dipolar electric moment of each particle and the total electric field at the particle position. This total electric field has different components: the incident and reflected at the interface field. The other terms contain all the scattering contribution from the particles. For these scattering terms, we use the second-order green tensor approach that evaluates the electric field at a given position generated by a dipole at different positions, with contribution from free space and scattered by the surface green tensor. We will present some of our latest results on forces on nanoparticles in the vicinity of an interface between two media, when we applied an external plane wave in the terahertz range. We analyzed the near scatter fields from the particles, especially the plasmon they excite at the graphene plane, and the forces they induce over the nanoparticles system. In this work, we study the forces pulling to pushing over one particle as function of the incidence of the plane wave in a total internal reflection scheme. In the color map, we show normalized total force in x direction as function of the angle of incidence for various distance from the graphene plane. B. In this work, we study the pulling and pushing force as function of the incidence from both sides of the interface, using in this case a metallic slab instead of a planar graphene. Normalized total force in x direction as function of the angle of incidence for various values at the goal thickness is shown in the right figure. C. Binding of a large number of particles in a linear arrangement with normal incidence. We show the distance between first neighbors as function of the particle number, a scheme of the system, a chain formed by any dielectric nanoparticles, and the last one, the energy barrier for the central particle as function of the total number of particles in the chain. D. Binding in two-dimensional range with normal incidence. Color map of the energy potential for only two particles, with one particle fixed at the origin and the other particle at the x and y coordinates. Schematic of the problem, and a color map of the energy potential for 5 particles, with one particle fixed at the origin and the others moving in a symmetric way, maintaining a rectangular structure as changing the up and right particle at x and y coordinates. Knowing the position of each particle, we solve a system equation and obtain the dipolar moment of each particle and the total field in each position. That let we evaluate the force that is acting over each particle. With these forces, we can resolve the dynamics problem to obtain the equilibrium position of the system. We start with a base distribution of 5 nanoparticles in a rectangular distribution with a width of 0.89 microns for the x side and 1.64 microns for the vertical y side, with a particle in the center of this rectangle. To obtain the equilibrium positions, we have solved the dynamical equation system, adding a drag force, and we studied the evolution in time up to the forces acting on all particles became 0. We can observe for 5 particles that the system goes to an equilibrium where both distances became smaller than the initial values. Then we increase with 4 bases of the rectangular with a particle in the center and so on. We show in blue the starting position of the particles and in red the final equilibrium positions. We study systems of 5, 13, 25, 41, 61, 85, and 113 particles, starting by one rectangle with a nanoparticle in the center, then 2 by 2, 3 by 3, and so on. This is one run of this calculation of the equilibrium position for one of the systems with 85 particles. We can observe that in the x direction, the system evolves first because this component of the optical force is larger, and in y direction is smaller and evolves slower. Although we observe that as the number of particles increase, the equilibrium of the system presents edge effects that become from the stronger relevance of the first neighbor's forces. These first neighbor forces are larger in x direction and smaller in y direction than the respective plasmon wavelength, and for this reason we observe different curvatures in the x and y edge effects. In the center of the large systems, we observe that the long-range forces found their equilibrium position at distance corresponding to the plasmon wavelengths, and because of this center part of the large systems present all the same similar distribution of the nanoparticles at the center of the array. Starting from the equilibrium position, we take advantage of the possibilities of changing the properties of graphene by applying an external voltage in such a way that we change the wavelength of the plasmons to be excited in the graphene. As we show that the equilibrium positions are related to the excited plasmons, we can change these positions and therefore the characteristic distance of our tunable optical matter. We can see how they change by increasing or decreasing the distance between the particles when we increase or decrease the chemical potential of graphene. It can be observed the variation along the x-axis is much larger than the variation in the y-axis in the same range of chemical potential changes. Owing to the short wavelength of superficial plasmon on graphene, near 20 times smaller than the photon wavelength at the same frequency, the interparticle separation in the formed arrays results much smaller than the radiation wavelength. In addition, this equilibrium separation can be dynamically controlled by chemical potential variations, a fact that highlights the use of graphene for optical binding applications. Motivated by the ability of plasmonic scattering to form deep potential energy wells, we demonstrate the assembling of a large number of particles into a two-dimensional array whose unit cell size is comparable to the surface plasmon wavelength.